Electrifying heavy transport comes with a massive physical penalty. To move large payloads over long distances, vehicles require enormous, heavily dense battery packs. That internal volume and weight directly cannibalizes the actual cargo capacity, destroying the vehicle's commercial efficiency. The engineering solution is dynamic power transfer. By charging vehicles while they are actively in motion, we can strip out those massive onboard battery packs entirely. We are seeing this take shape through inductive road infrastructure. In Sweden, the Smart Road Gotland project tested transferring energy to a moving 40-ton truck through coils embedded right under the pavement, aiming to push 125 kilowatts of power through winter snow and ice. But that inductive technology is still in its low-power infancy. If we look at established light rail systems, they handle significantly higher power loads using direct conductive overhead contact. Wireless energy transfer is conceptually elegant, but right now, maintaining a direct physical connection remains the only viable method for transferring megawatt-scale currents to moving multi-ton vehicles. This is the Sécheron SPL light rail pantograph. It is the modern benchmark for overhead conductive power transfer. The operational demands on this specific device are extreme. It has to safely transfer up to 1,000 amps of running current, and it must do so while maintaining constant physical contact at speeds of up to 100 kilometers per hour. That massive electrical load comes with a strict spatial constraint. The device must expand vertically up to 3.3 meters to reach the wire, yet be capable of collapsing completely into an aerodynamic 300mm flat profile on the vehicle's roof. To accomplish this, the pantograph functions as a highly tuned, reactive electromechanical suspension system. The core engineering challenge is bridging that 2.8-meter spatial gap with a folding structural linkage that guarantees uninterrupted high-ampere electrical continuity, no matter how the vehicle moves beneath it. We start at the roofline. Before moving a single arm, the primary requirement is physically isolating the 1,500-volt high-voltage overhead system from the grounded metal body of the tram. This lightweight steel-welded base frame mounts to the roof using 4 distinct heavy-duty insulators. Mounted to this base are the lower and upper arms. Their specific geometries govern the kinematics, providing the macroscopic spatial positioning of the entire device. These arms dictate the maximum vertical working limit, allowing the assembly to extend 3,300 millimeters above the roofline. Conversely, those same linkages allow it to fold down tightly, resting flat near the 300 millimeter mark when out of service. To shed weight, the arms are constructed from thin steel tubes reinforced by unstrained stainless steel rods. They pivot on insulated, maintenance-free bearings. The frame and arms effectively manage the spatial envelope. However, pushing 1,000 amps of current through those mechanical bearing joints would cause catastrophic heat failure. The structure provides the reach, but it cannot carry the load. The macroscopic arms have a second physical limitation: mass. At 80 kilometers per hour, the height of the overhead wire fluctuates rapidly. The heavy arms simply cannot react fast enough to these high-frequency micro-variations. If the pantograph bounces and breaks contact for even a fraction of a millisecond, that heavy current will arc through the air, instantly pitting and destroying the catenary wire. The solution is the pan head, the uppermost component outfitted with specialized carbon contact strips that physically press against the overhead line. The critical innovation is the independent leaf spring suspension system housing this panhead. By isolating the contact strips on the suspension, the panhead gains free, multi-directional micromovement. It keeps the carbon pressed firmly against the wire, completely independent of the slower, larger movements of the heavy arms below. To safely route the electricity down to the vehicle, thick, flexible electrical braids bridge the structural joints. This bypasses the mechanical bearings entirely, carrying the continuous current without charging the moving parts. Reliable dynamic power transfer requires this mechanical dual action. The large arm geometry spans the physical gap, while the highly sensitive panhead suspension guarantees the unbroken electrical connection. How does a heavy transit system reliably trigger and control this massive mechanical deployment in freezing rain and snow without relying on fragile microprocessors? The system uses strict circuit separation. The 1,500-volt overhead traction power is entirely divorced from a safe, internal 24-volt direct current control circuit. Deployment is handled by this central drive unit, which pairs an electric linear actuator with a heavy main spring. The energy profile is highly efficient. It requires only 260 watts of nominal power to physically raise or lower the entire multi-ton rated linkage. The raising logic is hardwired. A 24-volt signal activates relay K01 and switch S1, driving the cylinder outward. To lower the system, the circuit flips to relay K02 and switch S2, reversing the actuator's path to collapse the geometry. This hardwired logic governs strict temporal thresholds. The mechanism must complete a full raise or lower sequence in exactly 10 seconds or less. Using simple relays and mechanical position limit switches ensures a much higher rate of fail-safe reliability in harsh exterior environments than complex software controllers. The most severe physical threat to an overhead transit network is an obstruction or a wire defect snagging the moving pantograph at high speeds. If an unyielding pantograph acts as a hook, it will tear down kilometers of fragile overhead tension lines and insulators before the vehicle can brake. To prevent this, it is equipped with its primary failsafe, the automatic dropping device, or ADD. The ADD physically links a trigger device located on the panhead directly to the linear actuator down on the base frame. Upon detecting an abnormal heady physical shock, the trigger forces an immediate, unpowered mechanical disconnect from the overhead line. The timing of this sequence is extreme. The panhead severs its physical contact with the wire in less than 1 second. Immediately following the disconnect, the system forces the entire pantograph to rapidly plummet back to its flat, 300mm profile in approximately 3 seconds. Designing an unpowered, purely mechanical trigger to override all electrical controls acts as the ultimate safeguard. It sacrifices the vehicle's connection to protect the structural integrity of the wider infrastructure grid. When we combine the base frame, the structural arms, the independent panhead, and the drive unit, we get a fully functioning SPL pantograph assembly. Once continuous contact is achieved at speed, that 1500-volt current has to be safely routed off the roof and into the vehicle's internal architecture. The high voltage flows from the flexible bypass braids, down through the insulated roof mounts, and directly into the primary line breaker box. From there, the electrical flow moves to the internal traction converter, which conditions the power and feeds the massive drive motors that propel the vehicle. Despite all the advanced downstream computing and power inversion happening inside the tram, every single watt of dynamic propulsion relies entirely on the mechanical integrity of the folding arms on the roof. Compare this highly developed conductive model back to the inductive smart road truck test in Gotland. Burying inductive coils under the pavement successfully eliminates physical hardware wear, but it faces severe electromagnetic transfer limits and prohibitive infrastructure installation costs. The conductive overhead model offers unmatched raw power capability. It sustains 1,000 amps of continuous running current with an overload capacity pushing 1,300 amps. Modern overhead charging remains a highly optimized, fail-safe protected electromechanical standard, refined over decades of heavy transit operation. Until wireless energy transfer can reliably and economically scale to megawatt capacities, the sophisticated kinematics and hardwired logic of the modern pantograph will remain the definitive engineering solution for moving heavy transit.